the seminar list. But this morning we're going to get going with Ken and let him take over to talk to us about grain drying.
Okay, good morning. Ken Hellevang, agricultural engineer from North Dakota State University, as it indicates here on the slide. And what we'll focus on today is some of the specific energy efficiency features of grain drying or selecting grain dryers. And I just gave a presentation yesterday, and what I told that group is that probably the most common call that I get right now is from farmers that have been out shopping for a new grain dryer, and of course everybody has the best grain dryer and it's the most energy efficient, and they're having trouble trying to weed through all of the information. And so we'll try to hit a few key points here this morning, things that people should consider as they're selecting grain dryers, or things that they can do with existing dryers to improve their energy efficiency. And as we're going along, if you have questions, feel free to try to interrupt or type in a question, and Scott can help me to make sure that we get those questions answered. The first thing that we can do to minimize the cost of drying grain is to let the corn dry out in the field. And our focus this morning will primarily be related to corn. And frequently we get asked questions as to what kind of dry down can we expect out in the field. And of course that'll depend on where we are located, what our climate is. What I have shown here in this slide is put together based on North Dakota conditions, which are a little bit cooler than through a lot of the Corn Belt. But what I was frequently asked is what kind of dry down can we expect? And when I started looking at trying to estimate what that dry down might be, many of the same principles or parameters that we would look at for dry down in the field after we've reached maturity is similar to what we would look at as far as the crop moisture use during the growing season. And so what I did was to look at the potential evapotranspiration calculation, and this is again, like I said, for North Dakota. Excuse me. We looked at what was the PET, or potential evapotranspiration, based on our North Dakota Ag Weather Network. And what I found was that there was a pretty good correlation between this potential evapotranspiration and the kind of drying that we might expect. As we look at North Dakota conditions, we're going to see very good drying during September, probably over 4 points of moisture removal a week. As we shift into October, we're still looking at some pretty good drying conditions, but as we start getting into the cooler temperatures, the higher humidities that we would see in November, we're getting down to the point where we can see very little moisture loss out in the field. And the numbers will, of course, like I said, vary from location to location in the United States. But the studies that have been done pretty much parallel this, and somewhere as we start getting temperatures that are approaching freezing on average, we're going to see very little dry down out in the field. And so as a person's trying to decide what to do as far as letting it dry in the field versus combining it and drying it, most of the studies that have been done will indicate that by the time we get into probably middle to the latter part of October is time where we're starting to see limited amount of field drying occurring. We've seen a lot of interest in natural air drying over the years. One of the things to keep in mind with natural air drying is that it is extremely energy efficient as long as we design the system and manage that system correctly. I've seen systems that work very well, and I've seen systems that are very inefficient. And again, one of the challenges that we face, particularly with corn, is we're getting later in the season. As the outside temperatures get colder, the moisture holding capacity of that air becomes less and less, and the ability then to dry becomes less. And what we frequently will look at is, well, should I just run my natural air drying system, or should I be adding some supplemental heat? And what I normally will tell people is that if we're concerned about drying speed, basically we're looking at airflow, regulating that drying speed. If we're looking at changing the final moisture content of the grain, that's when we start looking at supplemental heat. But one of the challenges that we face, whether we're talking wheat earlier in the season or corn later in the season, is that potential for over-drying. And this slide is showing the potential for over-drying wheat, looking at an initial moisture content of 17%, an airflow rate of 3/4 of a CFM or cubic foot per minute per bushel on a 10,000 bushel bin. 10-cent electricity, $8 a bushel wheat, and assuming again a North Dakota climate. If we're looking at average September conditions, will dry based on outdoor conditions to about 14.5% moisture, which is too wet. But one of the things that we need to keep in mind as we're designing and operating this system is that we're always going to get a little bit of supplemental heat off of the fan. The amount of temperature rise is going to be related to the static pressure that fan is operating against. We've typically used a rule of thumb of at least 3 degrees. Frequently with the static pressures that we'll see working with wheat, we might be 4 or even 5 degrees of temperature rise. And so in September, even though the average conditions don't quite get us to the 13% or 13.5% moisture that we want, when we take into consideration that fan heat, it does bring us down to the moisture content that we want. If we were to add supplemental heat, and 10 degrees doesn't seem like a lot, brings us back to 70 degrees, but drops that relative humidity down to 41%, and all of a sudden, rather than having 13.5% moisture wheat to market, we're now looking at 10.8% moisture. Really haven't speeded up that drying time, but when we start looking at the costs associated with that added supplemental heat, we're looking at a shrink cost of about $2,400, the heat cost of about $1,500, and almost $4,000 on this 10,000 bushel bin of wheat for adding supplemental heat when we really didn't need it. Even as we go into an average October or cold September in our climate, if we're looking at adding 10 degrees of supplemental heat, we're still looking at over-drying the wheat, and we're looking at some pretty substantial costs. If we're looking at very humid September conditions, we're looking at maybe the fan heat not quite getting us down to the moisture content we want. If we add 10 degrees, again, we're over-drying. Just a 5-degree temperature rise will bring us to roughly 13% moisture and minimizes those over-drying charges. So there's probably places where this rule of thumb will not apply, but in general I say that about a 5-degree temperature rise is all that we will need, and we'll even look at that as we look at corn. As we look at corn in North Dakota, we're looking at an October harvest. October average conditions with the 3 degrees of heat off the fan and we're drying to about 13.5% moisture in about 42 days. As we go later into the month and the temperatures start cooling off, if we don't start until the 15th of October, we've seen a huge drop in temperature and an increase in relative humidity. Still, the moisture content isn't too bad, but we see the days required to get that drying done going up considerably. As we go to November, where we're looking at our average temperatures here being down near 30 degrees, what we see is that we're clear out to about 70 days of fan time to get that dry. So even in November, if we add 10 degrees of supplemental heat, what we see is that we're dropping the corn moisture content down to 12.5. Again, we're facing an over-drying charge, and we've speeded up the drying a little bit, but we could run the fan and the heater both for the entire month of November when we have temperatures near that freezing temperature and only get half of that bin dry. So the natural air low temperature drying works very well until we have temperatures that are dropping below about 40 degrees. As we start approaching freezing temperatures, the natural air drying or low temperature drying just becomes inefficient. And so that's a critical point as people are making choices on which drying system to work with. What I recommend for a lot of farmers is to hold that corn cold over winter, bring it down to temperatures right around freezing, hold it over winter, and then in the spring when we start seeing temperatures that are up close to 40 degrees on average, then we can turn the fans back on and do the drying. And when we look at climatic conditions across the country, what we will see is that spring drying conditions really are pretty good. If we look at May conditions here in North Dakota, we're looking at an average temperature of 56 degrees, 60% relative humidity. We're able to dry the corn down to the moisture content we want for summer storage, and we're doing it in about 43 days. Natural air low temperature drying, if it's sized correctly, managed correctly, is going to be the most energy efficient. And so harvesting the corn, holding it over winter, doing the drying in the spring when temperatures start averaging around 40 degrees or warmer is a very viable option. It does make a difference which fan type that we're using to move the air through the grain. And there's 4 different types of fans that we will typically use for moving air through grain. We have the axial or propeller type fan. We have the inline centrifugal fan, which is this one with the bell-shaped inlet and still the round axial fan type housing. A low-speed centrifugal fan operating at 1750 RPM, and the high-speed operating at 3500. And if we look at a bin of corn, 27-foot diameter, 20 feet deep, 10 horsepower fan on that bin with an axial flow or propeller type fan gives us 0.95 CFM per bushel. The inline centrifugal about 0.79, the low-speed centrifugal 1.1, and the high-speed centrifugal 0.64 CFM per bushel. So the vast majority of the bins now today are being built with the low-speed centrifugal fan on that bin just because that's going to move the most airflow per horsepower. If we kept the depth a little bit shallower, the axial flow fan works just fine. The low-speed centrifugal fan gives us the option for those folks that are in regions of the country where you might be doing wheat and corn or crops that have a little more resistance to airflow. The low speed works well on both applications. I mentioned that the depth of the corn has a big influence on the airflow and the energy efficiency of that system. What we have heard over the years is kind of a rule of thumb of 1 horsepower per 1,000 bushels. And that works fine as long as we're looking at an airflow rate of about 1 CFM or cubic foot per minute per bushel. As we're looking at an 18-foot or just a little over 18 to 19-foot depth, that 1 horsepower per 1,000 works fine. But as we start going to greater depths, as we go up to a 20-foot depth, we're up to 1.1. 22-foot depth up to 1.3 horsepower per 1,000, and at a 24-foot depth we're up to 1.7. So we start losing the efficiency of our drying system very quickly as we increase the depth, and I typically will recommend that we limit the depth on corn to somewhere in that 20 to 22 foot. As we get beyond that, we're starting to use so much horsepower that we're not energy efficient anymore. The same thing is true as we increase the airflow rate, going from an airflow rate of 1 CFM per bushel up to 1.25 CFM per bushel increases that horsepower requirement from 1.1 to 1.8. And so we're limited to approximately that 1 CFM per bushel if we're going to go on a full bin of corn. So just a few years ago, we were seeing a lot of bins that were being installed in this area. They were putting up 42-foot diameter bins with a 36-foot sidewall depth, and farmers were wondering, can I dry corn in that bin? And when we looked at providing that 1 CFM per bushel airflow rate that's required, we would need 180 horsepower to get that job done. And so, of course, that isn't realistic. It isn't practical to put that kind of horsepower on a bin. And so if they're going to do air drying, natural air drying, ambient air drying in a bin, we really do need to keep that depth down to roughly that 20, 22-foot depth to stay energy efficient. If we look at high temperature drying, there's a multitude of options, and we'll just very quickly walk through some of those options. If we're doing a stirring batch bin drying, typically we're looking at a fairly shallow depth of corn, maybe 6 to 9 feet of depth. We're looking at airflow rates then are somewhere in the 8 to 15 CFM per bushel. The way to get the maximum performance out of that type of a drying system is to keep that depth shallow. They may tell us that we can add more depth in here and use this as wet holding, but when we do that, we're going to reduce the amount of airflow and reduce the drying capacity considerably. The other thing with virtually all of our high temperature drying applications is we want to use the maximum temperature that we can that will not damage that corn. That's the way we're going to get the most energy efficient drying. And in this case, typically we're looking at drying temperatures maybe up to around 160 degrees Fahrenheit. But I always tell people, at least as a starting point, look to the company that you're buying the equipment from for their recommendation on what that drying air temperature should be. We also have a continuous flow bin dryer. In this case, the grain is swept off the bottom with the sweep augers, augered up out of the drying bin into an adjacent bin where the cooling is done. Again, we're looking at a depth probably of 6 to 8 feet is where you're going to get the best performance out of this bin. Normally when we would think about it with this depth of corn, we're going to get good air saturation as the air goes through. we would expect it to be a very energy efficient drying system. I've done a couple of energy audits on these systems and have been surprised to find that they weren't as energy efficient as I would have expected. And it just really emphasizes that we're really looking at two things when we start talking about energy efficiency with any of these drying systems. It's the design portion and then the management or operation application of that dryer. And particularly in these dryers, if we're backing off on the air temperature or doing other things that increase the energy efficiency, we will very quickly find out, even though that we have the depth being such that we would expect good performance, because of the management, we may not get the expected performance out of that dryer. Kind of the standard cross-flow dryer can be represented with this diagram, where we have the heated air coming into the center. It goes through the corn column and exits out the side. Corn that is going to be on the inside of that drying column will be at a much lower moisture content and a higher temperature. That's on the exterior will be at a much higher moisture content and lower temperature. And so with this style of drying, typically we would expect a drying energy efficiency or energy use of about 2,500 BTUs to take out a pound of water. But we're going to see a fair amount of moisture variation, temperature variation across the dryer. And so we've had a lot of modifications to this old standard batch dryer to improve both the performance from an energy efficiency standpoint, as well as to improve the corn quality coming from that dryer. And we're going to look now at several of those items. This is a graph that I show in virtually all of my presentations based on some research that was done quite a few years back, where they looked at the energy consumption based on the various airflow rates and the various drying temperatures going through a cross-flow dryer. And what we see, of course, is the higher the airflow rate, the more energy is required, because the air is moving very rapidly through that drying column. But the other thing that shows up is that we definitely see a difference in energy consumption as we vary that drying temperature. And that's really where this fundamental principle of to get the most energy efficiency out of the dryer, we need to use the maximum temperature that we can without damaging that corn. Now, some of the dryers, a lot of them today are up in the 70 to 90 CFM per bushel airflow rate. And we'll look a little bit later at the mixed flow dryer, which is just under 50. That's about 45 CFM per bushel. And then, of course, the in-bin dryers, which this really wasn't, the research wasn't done on that style of drying, but at this lower airflow rate, I think we can get the indication, again, that there's an optimum point for energy efficiency on the in-bin dryers, and that's roughly associated with that recommended 150, 160 degree temperature that we're using in those dryers. We're just going to quickly walk through some of the different options that are available with dryers today, and look at, again, both the performance of that dryer as well as the energy efficiency of that dryer. Kind of the basic fundamental dryer is the heat and cool batch dryer. And as I indicated earlier, the grain or corn on the inside of the wall is going to be at a much warmer temperature than the corn on the exterior. And we'll typically see a loss in grain quality and energy efficiency in comparison to the other types of dryers. So here we run the full dryer in heat, complete the drying, and then switch the burners off and run the cooling cycle to cool that corn down. Now as we start looking at some of the continuous flow dryers, the pressure heat, pressure cool dryer is going to be essentially the same as that batch dryer, except now we have this floor in here so that the top portion is heated, the bottom portion is the cooling portion of the dryer, and again we see essentially the same characteristics that we had with the batch dryer. We've seen a lot of dryers be used as full heat continuous flow dryers recently. And part of the reason for doing that is it gives us the best capacity in bushels per hour, because we're using this entire dryer under the heat mode, so we're drying in that whole dryer. We take the corn out of this dryer at the bottom of the dryer, so we're not doing any cooling. We're probably looking at kernel temperatures of 110 to 130 degree kernel temperatures that come out, be dumped into a bin, and then we do in-bin cooling. And so it's important that that aeration system for the bin be sized to be able to cool that corn adequately, and there's going to be some moisture removal that takes place. The moisture is still being moved from the inside of the kernel to the outside of the kernel as long as it's got the heat of the kernel there, and so we see a lot of moisture removal. One of the efficiency benefits that we get and quality benefits that we get with this type of system is that the final points of moisture are the most difficult to remove. And so rather than taking those last 2 points out in the high temperature dryer, what we're doing is dumping this dryer at maybe 17% moisture and moving that corn into the bin, cooling it a little bit slower in the bin, and in that cooling process we're picking up a couple points of moisture removal. So we increase in speed, we increase in corn quality, and we increase in drying efficiency. There's a 2-heat continuous flow dryer. Here both the top portion and bottom portion are heated. We run the lower portion of the dryer at a cooler temperature to try to maintain the corn quality, and we'll see a slightly better corn quality coming out of this dryer than if we were running the whole dryer at the same temperature. But we do see a little loss in the energy efficiency because of the cooler temperature in the lower portion of that dryer. We're still dumping hot, so we still need the same attention related to aeration and moisture management in the bin as we're doing that cooling process. As energy costs increased, we've seen a lot of interest again in what is called a pressure heat, suction cool, or vacuum cool type dryer. Here in the lower cooling portion of that dryer, now the air is being pulled from the exterior through the corn. That air then is cycled back to the intake of the fan, and that is blended then with outside air. So we're preheating the air that goes through the burner and into the dryer. Capturing this cooling heat can increase the energy efficiency by maybe as much as 20–25%. We're going to see just a slight reduction in the bushels per hour because we're not using the entire dryer for drying at this point, but we're seeing a significant energy efficiency gain by capturing this heat. Now, when we compare the energy efficiency of doing the cooling in the dryer versus doing it in the bin, they're going to end up being fairly close. Here we're capturing the heat, but we're doing it immediately as part of the dryer, so we don't see probably as much moisture reduction as what we might with what we call dry aeration, and we'll cover that a little bit later. As I indicated, this vacuum cooling can increase drying energy efficiency by 20, some will even say up to 30%. There's been a lot of tower dryers that have been sold based on that principle, because we're pulling the air in through the bottom portion, up through the burner, and out through the top. That same principle works, though, in a horizontal dryer as well. Whether we put the fan inside the dryer as this one shows, or if we have it exterior as we've been showing previously. So a huge benefit, particularly I think for those of us that might be in the northern part of the Corn Belt, that as we're looking at cool outside temperatures, being able to capture that heat rather than just exhaust it to the outdoors makes a big difference. The last dryer that we will look at is the pressure heat, suction cool with heat reclaim off of the final portion of the dryer. And so now in this case we have a shrouding or housing around the lower portion of the drying column. And what we're doing then is not only capturing the air coming through the cooling portion of that dryer, but also that final drying stage of the dryer. Cycling that back through the fan and being used then to preheat the air going into the rest of the dryer. This is by far going to show the best energy efficiency. We're dumping the corn cool out of this dryer, so it does not require near the management of in-bin cooling, and we'll go through that in a little bit later. Now, how do all of these different systems compare? And this is information from one company. All of the slides, as you've been seeing, have been looking similar because they all came from one manufacturer. One company has all of these different options for their dryers depending on how you want to set up your system on your farm. What they did was to go through and look at how they compare from a fuel cost standpoint, assuming $1.85 propane, 10-cent electricity, and a 5-point moisture removal. If we look at the pressure heat, pressure cool, they were saying we were looking at about 16 cents to do the 5 points of moisture removal. Going with a full heat dryer, reduce that to 13 cents. The pressure heat vacuum cool ends up being essentially the same, maybe just a shade better. Now again, when they say full heat, they're assuming we're dropping the corn at 17% moisture and taking out those final points in the dryer, in the bin, using an aeration system, and they're including that as part of the energy efficiency calculation or cost that they calculate. The pressure heat, vacuum cool, heat reclaim down to 9 cents. So even though this one is going to be the most economical from a drying cost standpoint, my experience at least, we don't see very many of these actually being used. They will reduce the drying capacity just a little bit, and we see most of the systems either being full heat or pressure heat with vacuum cool. There's been a number of improvements in grain dryers over the last few years that I really encourage farmers to take into consideration as they're selecting a dryer. Some of these give us benefits both from an energy efficiency standpoint as well as a grain or corn quality standpoint. The stage temperature dryer, here we're doing essentially the same thing that we were doing with the 2-heat dryer. We might be running the top dryer up here at a much higher temperature without damaging the corn quality because of the evaporative cooling. And then the lower portion of the dryer, we back off on the temperature so that we don't damage the corn quality. We go with what is called a grain turner or grain inverter, and this has become extremely important in our dryer design. What we're doing here is taking the corn that was on the inside of the column and moving it to the exterior of the column. Taking the corn on the exterior and moving it to the interior. So we no longer have all of that corn staying on the inside or the exterior. It gives us much more uniform moisture contents. The corn isn't exposed to the high temperatures for the extended period of time, and this has been a huge improvement in the grain quality as well as energy efficiency. So something either of a grain turner or grain inverter is something that I really encourage people to look for. Now there's other options that are being done by different companies that attempt to do that same result or get that same result. This is a dryer where they use multiple metering rolls, and so they're removing the corn from the inside of the column much more rapidly than the corn on the outside of the column. And so again, we're blending and mixing the corn together to get more uniform moisture contents. This is again from another company where they use a diverter in that grain column, so the corn on the inside moves more quickly or faster than corn on the outside. What they indicate is more moisture uniformity as the corn goes down through the dryer. What they have observed is when they compare the dryer with this feature to the dryer without that feature, that we're seeing a 1 to 4 pound increase in test weight or difference in test weight between having this feature and not having that feature. So that's an indication that by speeding that corn down the inside of the column, we're more gentle on our drying process and not damaging the corn near as much. It also allows them then to increase the plenum temperature 10 to 20 degrees. And their rough rule of thumb is that a 10-degree temperature increase results in about a 4% energy savings. And again, that makes sense as we go back and think about that graph that we looked at earlier. It also gives them about an 8% increase in drying capacity or in bushels per hour. And so one of these features, either the inverter or the metering rolls or these diverters, are something that farmers really should be considering from an energy efficiency standpoint. Another thing that we will see in some dryers is that they're varying the width of the column. And here in the initial portion of the drying column, they're going with an 8 to 12 inch heat zone. And of course, this is where the corn is going to be at the highest moisture content. The air becomes more saturated quickly, and therefore, by having a narrower column, once that air is saturated, it's not picking up any more moisture, and so it's being exhausted to the outdoors rather than going through the rest of the corn. It also causes more of the air to go this direction because the air takes the path of least resistance. A 12-inch heat zone and a 12-inch cooling zone in the dryer to help. And then you see these diverters that are in the dryer as well. Selection of the fan also is critical. What we're looking for in fan selection is to really look at what types of grain are going to be dried in that dryer, what kind of static pressures those fans will be working against, and then finding the fans that will move the most airflow at those operating static pressures or over the range that they're going to be working with. And this shows that it makes a big difference whether we're talking corn or we're talking wheat. And I realize for the majority of the country, corn is about all that we run through the dryers. But if you're in an area where you're drying more than one type of crop through the dryer, it's important to really think about, will that fan be able to efficiently move air at both static pressures as we're drying that grain. Another type of dryer that we're seeing more and more of is called a mixed flow dryer. And the reason that we call it a mixed flow dryer is the air comes out through these channels from the inside, and some of the air then will exit by traveling against the flow of grain up to the adjacent channel up above where the air comes out, or it may flow concurrent with the grain and come out at the channel below. And so the grain is constantly moving down, the air is constantly coming in at all of these different locations through the dryer, and we end up with the grain or corn not being exposed to the hot temperatures for an extended period of time. Because of that, it ends up being a good dryer to maintain the grain quality. This is also the dryer now that is operating at about 45 CFM per bushel of holding capacity, where the traditional cross flow is going to be closer to the 70 to 90 CFM per bushel. That makes this dryer quite energy efficient. And the common question is this dryer then more energy efficient than the cross flow dryer? And my answer to that always is that when a cross flow dryer incorporates their energy efficiency features, some type of grain diverter, grain inverter, plus some type of heat reclaim, whether it be in-bin cooling or whatever, that dryer then can become fairly energy efficient as well. This dryer typically, from the numbers that I'm hearing, is going to be quite a bit more expensive than a traditional cross-flow dryer. So we're seeing some farms and elevators that are investing in these dryers. They have worked very well. Some of them refer to them as screenless dryers. Others really question whether you have enough benefit in energy savings to pay for the increase in costs. But if you're comparing the two dryers, and the cross-flow dryer incorporates all those other energy efficiency features, it's likely approaching the same energy efficiency as this type of dryer. One of the things that sometimes I think gets overlooked is that the colder the outside temperature, the more it's going to cost to heat that outside air, and the more expensive the drying becomes. And so this needs to be balanced against that first slide where we talked about leaving the corn in the field to dry down. And frequently what we find is that we're better to start harvesting that corn as long as we're in the low 20% moisture range, do some of this drying when outside temperatures are much warmer, and then eliminate drying when it's very cold. Particularly, again, for those of us that are in the northern end of the Corn Belt, where we can see outside temperatures that some years might be down near zero, that's going to increase our drying costs considerably. But again, if we can capture some of that heat with air recirculating, whether it's some type of vacuum cooling or whatever, that's going to improve some of that energy efficiency as well. As we've worked with dryer efficiency over the last few years, we've come across claims sometimes that are almost more than you can believe. And so I think it's helpful sometimes to see what would be the best energy efficiency that we would be able to obtain. And this is a chart that or table that I copied out of one of my public drying textbooks by Drying Cereal Grains by Baker Arkema Hall. And I think it's important for us to look at really what would be 100% energy efficient. If we were just vaporizing water, we're looking at roughly 1,100 BTUs required to evaporate a pound of water. If we look at corn, we're probably somewhere in the neighborhoods of about 1,200 BTUs as being 100% energy efficient as far as the energy required to evaporate a pound of water. And so from a grain drying standpoint, I think a realistic expectation might be something in the neighborhoods of 1,500 BTUs as being about as good as we could expect to obtain. Now, we've had dryers that have had claims as low as 1,100 BTUs to take out a pound of water. And I've challenged that's just not going to be practical or realistic. In the conversations I've had with some of the dryer manufacturers, they seem to be pretty much in agreement that this 1,500 is probably the optimum that we could obtain. In reality, I think most of the time we're going to be closer to maybe 1,800 BTUs, maybe even as high as 2,000 BTUs to take out a pound of water, depending on what outdoor temperatures are. I mentioned several times when we were going through the dryers that several of those drying systems require that we cool the corn in the bin in order to obtain that energy efficiency. We're going to look at two different options for cooling in the bin. The first one is dryeration. Here we're dumping the corn hot out of the dryer. It sits without airflow or sits warm for 4 to 6 hours. It doesn't necessarily have to be without airflow, but we can't do the cooling for 4 to 6 hours. During that time, the heat within the kernel continues to move the moisture to the outside of the kernel. Then we turn the fan on and cool the corn and pick up that moisture. During the time, both that we're doing this tempering as well as when we're doing the cooling, there's going to be extensive amounts of condensation occur. And so it's critical that we move that corn then from this dryeration bin to a different bin for storage to mix up the wet corn with the dry corn. As a rough rule of thumb, I say that we're looking at about 1/4 percentage point of moisture removal for every 10 degrees that we cool that corn. So typically we're looking at maybe 2.5 points of moisture removal during this dryeration process. Some of the benefits that we've already talked about by doing the cooling in the bins, we're increasing the dryer capacity by 50 to 70%, and we're reducing the energy consumption by 15 to 30%. So when you make this comparison to what we're looking at with some of the other drying systems, this is considered in as part of that energy savings. The other option that we have is called in-storage cooling. And here, rather than leaving the corn sit for that 4 to 6 hours before it's cooled, we're cooling the corn immediately. And to do that, we need an airflow rate of about 12 CFM per bushel per hour of fill rate. So if a person is drying at 100 bushel an hour and putting into this bin, we need 12 times 100 or 1200 CFM of airflow in order to cool that corn roughly at the same rate that we're filling the bin. We're going to see about a point or a point and a half of moisture removal because we're not tempering. We don't see quite as much moisture removal. Now with in-storage cooling and with dry aeration, but particularly if we're talking about in-storage cooling where we're not moving the corn, it's critical that we be concerned about the amount of condensation that's forming in this bin. Two things that a person needs to keep in mind. The cooler the outside temperature, the more potential we're going to have for condensation. If you look back at some of the early work that was done on in-storage cooling, they did not recommend that we use in-storage cooling when outside temperatures were below 50 degrees. For a lot of the corn country today, we do a lot of drying and cooling at temperatures below 50 degrees. For those areas, I think it becomes critical that we do partial cooling in the dryer. Maybe run the cooling portion of the dryer and cool that corn down to about 90 degrees before we put it into this bin. That way we minimize the temperature differential and reduce the potential for condensation. As a person is making a decision on their drying system, I think it's important for them to really get a grasp on what their current energy use is. I've been involved with roughly 50 energy audits and find it very useful to just stop and calculate out how much energy is being used. It may be that our management strategy isn't correct, and we need to change how we manage this drying system, and that can improve the energy efficiency. It may be beneficial to change dryers, but I think we need to know first where we are with our existing systems. So as part of the energy audit, we're looking at determining what our current energy use is, trying to determine what the energy use would be of the new system, figuring out then what the savings is and what the payback period is. Does this make sense? And I've got just an example that I have done here. For one individual, he was drying 239,000, roughly 600 bushels of corn. The average moisture going in was roughly 23.7%. Coming out, it was at 14.7%. So we went through and calculated the water removed from that corn at 6.5 pounds. Now, it's important that we keep in mind that this is not a typical shrink calculation. I've seen some audits done where they just use a standard shrink number percentage-wise, and that doesn't give you the right number. You need to go through and calculate what the wet weight would be and then what the final weight would be and subtract those two. His fuel usage was 45,916 gallons of propane, So a little under 0.2 of a gallon per bushel. You could calculate the energy used then per bushel, do what the weight was of water being removed, and therefore he was looking at roughly 2,700 BTUs to take out a pound of water. So looking at his existing system, we would say there's probably things that he can do either from a management standpoint or in selecting a dryer that will improve his energy efficiency. Most of the companies that are selling dryers today have the ability to do energy analysis. They have simulation programs. You let them know what outside temperatures and relative humidities are going to be, how you intend to be operating the dryer, and they then will go through and calculate out what the energy efficiency will be. In this case, this dryer was showing 1,964 BTUs required per pound of water removed. Each company has kind of their own system of doing the calculations, but the program output is going to be similar. Now, on this tower dryer, it was showing their energy efficiency at 1497, so down pretty close to that 1,500 BTUs that I talked about. What I would then encourage people to do is to keep in mind that here they're looking at 50 degrees as the outside relative humidity and 50%, 50 degrees outside, and see is that realistic for the conditions that I'm going to be drying at, and then realize that this is just indeed an estimate and maybe a little bit optimistic. So I've covered a lot of territory here in the presentation, but hopefully hit some of the key energy efficiency things that a person should be looking at. I have a fair amount of information, as well as other places have information up on the web. My material can be found by doing a search for NDSU grain drying and storage. So with that, I'll open it up and see if there are any questions.
Anybody have any questions for Ken? I think we may have one coming in. Oh, will the slides be made available? Yes, we'll send them out with a copy to the recording here later on this afternoon. Any other questions? So you might have something else coming in. Well, I'm not seeing any other questions coming in. If you have additional questions, you could email them to Ken or myself, and we can, oh, wait a minute, here we got another one. Low temperature generally means lower humidity. Does that factor into your thinking?
Typically what we'll see at lower temperatures is higher humidities as we look at most of the area where we're drying grain. As we get later into the fall and we're looking at cooler temperatures, we're looking at a little bit higher humidity. When we're talking natural air, low temperature drying, the primary thing is the outside temperature. Humidity has a little bit of effect as far as the final moisture content, but not a whole lot. When we start looking at a high temperature dryer, temperature and relative humidity does have a little bit of influence, but when we're taking outside air and heating it to 200, 230 degrees, the effect of the outside humidity ends up being fairly minor, and so typically isn't a major consideration when we're talking about high temperature drying.
Hopefully that answers the question. As I was saying, if anybody else has any other questions for Ken, you can email them to myself or Ken, and we'll try to get them answered for you. Otherwise, we'll call it a day, and we'll be sending out an evaluation along with slides and recording link later on today. Thank you, and have a good day.